For inviting me to participate. It's been a great pleasure to be here. This is my first visit to Korea, so I'm very happy to be here. As Juan said, the title of the talk is Avoidance Behavior in Intraguild Predation Communities, a Cross-Diffusion Model. I'm the second author. The lead author on this paper is my former student, PhD student, Daniel Ryan, who is currently at the National Institute for Mathematical and Biological Synthesis at the University of Tennessee. And these results are a slight elaboration of some results in his thesis that we've recently submitted as a paper. And so the topic here of the day is intraguild predation, and I use IGP to represent intraguild predation here. And it's the situation where a predator and a prey also compete for shared resources. Things that compete for resources in ecology are spoken of as being in guilds. And so this means within guild predation, so that within guild, one organism is either preying on a species or at least attacking it to prevent it from sharing the resources, which could be an extreme case. It is what's called an ecological module, and it is one that occurs rather widely in nature. And here I give references here where I just have the names of the author and the journal and the year. I have the paper with me, so if anyone wants a more detailed reference to anything, I'll be happy to provide it to you. The first significant modeling that I'm aware of this was by Bob Holt at the University of Florida and the late Gary Polis, who studied a 3-species ODE model. And what they found was that it was rather hard to get coexistence in the models. That for the very frequently under situations where they were expecting to see coexistence, one or more of the species would go extinct. Okay, so they discussed in this article various ways that you could mitigate to see this kind of phenomenon, because as I said, it occurs fairly widely in nature, and they suggested various mechanisms, but one of them of most interest here is going to be environmental heterogeneity. Okay. Consequently, and simultaneously, you see various empirical studies that were suggesting the role of environmental heterogeneity, namely that what happened is somewhat of a spatial segregation phenomenon where the interguild prey, that is the intermediate species, is going to locate in regions where the resources are less good, therefore less attractive to the IG predator, and so that the trade-off being that you're not getting as good a resources, but you're not getting eaten yourself. So so you have that balance. And again, this was observed to occur across a wide range of taxa, from mammals to birds to insects to bacteria. So there is empirical evidence here was being formulated that environmental heterogeneity is a likely explanation for the widespread nature of interguild predation communities. Priyanka Amasakare at UCLA was the first to model interguild predation in a heterogeneous environment, and she used a 3-patch model with 3 ordinary differential equations for each patch, and then movement between, and so a system of 9 equations that she studied numerically. And she studied first random movement strategies, and then later non-random strategies that she termed density dependent, habitat dependent, and for our purposes most relevant, fitness dependent. I should say when we were working on this project, I was convinced that the development of cross diffusion was such that we would be able to use that as long as we were in a so-called triangular system. And then when we got started, I was trying initially to suggest that we should follow something more along the lines of SKT, but that didn't really quite work. And then Priyanka came to visit us, and Dan honed in on this idea of fitness-dependent dispersal, and that sort of is the key feature of being able to make this work. And so our model is the following. So it is we have a, let's see, is this the, okay, good. All right. So we have a bounded habitat patch. Notice here we are at present restricted to 2 space dimensions in what we do. A former student of Chris Cosner is currently working on extending some of these ideas to habitats that are in 3 space dimensions, but it's not quite got the results there yet. This has to do with getting the global dynamics of the problem. Okay, but so the habitat domain is in R2. It's bounded with a smooth boundary. U here will be the density of the resource. V is the density of the IG prey, and W is the density of the IG predator. You have basically just random motion for the resource species and the IG predator, whereas here we've got a nonlinear diffusivity for the IG prey, and this is going to end up being thought of as being fitness dependent here. Notice I've got Neumann boundary data on each species. I'll comment on that in just a minute more. So then we have here also then our fitness terms, okay, for the resource, the IG prey, and the IG predator. And these are given in fairly standard kinds of terms. For the resource, we necessarily have to have some underlying spatial heterogeneity, and so that comes in through this per capita intrinsic growth rate term, R of X. Then we've got a self-regulation term. We have those for each species. Then we've got basically Holling 2 type functional response throughout, where here AI will be the attack rates, HIs will represent handling times, and the EIs represent conversion efficiencies. And notice here that we have linear mortality terms for both the prey, IG prey, and the IG predator, but we also have to have self-regulation in terms of being able to get all of our a priori estimates to work out properly. Okay, so again, a little more on the parameters. Again, pure diffusion for the resource and the IG predator. Again, spatially varying resource productivity, positive throughout, C alpha for some alpha and 0, 1. Our natural mortality, self-limitation or overcrowding coefficients, attack rates, handling times, and conversion efficiencies. And the function M of U and W, which is the IG prey motility, at this stage we're just going to insist that it be twice differentiable with M of U and W bigger than or equal to D, bigger than 0 for all U, and W bigger than or equal to 0. We can prove global existence of solutions without specifying the form. Later we will specify in terms of a fitness-based avoidance strategy that will allow us to assert the persistence of the IG prey. Okay, as I said, we have assumed here Neumann boundary conditions, but notice here that if we look at the outer normal derivative of this flux term, we get, by the chain rule, we get the following. And what we see here is that Neumann boundary conditions implies that we've got no flux conditions on this term, and likewise, if we've got no flux, we see here since the partial of U with respect to eta and the partial of W with respect to eta is 0, that no flux does imply that the outer normal derivative of V is equal to 0. So Neumann boundary conditions here are equivalent to no flux. Okay, so some comments on global existence and a compact global attractor. So we're going to work in the space W1P cubed, so space of triples in W1P with the norm, the sum of the W1P norms of the three components. Here we're in R2 is our underlying spatial domain or spatial dimension, and so P bigger than 2 will imply that this will embed into C of omega, so our space will be the cone of triples of non-negative functions in this, which are necessarily continuous functions. So the classical results of Ammann about quasi-linear problems from in nonlinear analysis, mathematical Zeitschrift, and differential and integral equations prove global existence results for a class of quasi-linear parabolic problems that include ours. And Theorem 1 of the mathematical Zeitschrift paper implies that if P is bigger than 2, there's a unique classical solution to the problem corresponding to an initial density configuration in our space. And this solution will exist on a maximal interval in time, and Ammann showed that if the L infinity norms of all components are bounded for T in this interval, the interval is 0 to infinity. And then standard comparison principles for single parabolic equations with coefficients that depend on space and time can be applied to conclude solution coefficients remain non-negative. Dungley, in a paper in the Indiana University Mathematics Journal, proved some stronger results for a two-component system with additional assumptions bounding the growth of the flux and reaction terms. And Lay's system included just one component with dispersal described by cross diffusion and one with random dispersal. So this is in the so-called triangular cross diffusion context. And we argue how the proof can be extended and adapted to prove global existence of solutions to our system. Here, P is equal to 2, P greater than or equal to 2 here, and that viewed as a semi-flow, we will have a compact global attractor. The key here is that only one component in our system disperses in a random way, and then what we have to do is get an ultimate uniform bound in L2. Then the results in Lay will allow us to get an ultimate uniform bound in L infinity for all three. Hence, then we can apply Ammann's results. So, our first theorem states that if U, V, and W are is the unique classical solution to the problem corresponding to initial data in W1P plus cubed, then the solution will exist for all time, and moreover, there will be an alpha in 0, 1, so that the C1 plus alpha norms of each of the components are ultimately uniformly bounded. Consequently, the system will define a semiflow on W1P plus of omega cubed, and this semiflow possesses a compact global attractor. So just some comments here. The C1 plus of omega closure embeds compactly in C1, which will embed continuously in W1P, so that this enables us to say that the semiflow is point dissipative. And then theorem 1 of Ammann from the mathematical Zeitschrift paper will tell us that pi dot fixed at t will map continuously into C2 cubed, hence compactly into W1P of omega, so for t greater than 0. So you have the two conditions that are required to apply the classical result of Bilotti and LaSalle to assert the existence of a compact global attractor. So, motility functions modeling avoidance. So we're going to assume that the IG prey is able to assess local quality, okay? And again, empirical evidence suggests that this is valid across a spectrum of organisms from a wide variety of taxa, that they're able to determine local resources and determine the frequency of predator attacks, and thus be able to then move so as to go towards where the balance between the two forces is best. And so the fitness function then gives a good surrogate for being a measure of this kind of advantage. And the limitation of our mathematics is that we can't directly use the fitness function per se, because that would require us to have the motility m that multiplies v to be dependent on u, w, and v, and we can't handle mathematically if it's got a v in there. So what we do here is we replace the g with g star of u and w, which is g of u 0 and w, and set m of u and w equal to m of g star of u and w. And the focus of all of this is that the intraguild prey is going to be able to invade the system when rare, so that the fitness that is given when it's at 0 is a good approximation by this g star function. And I should also point out, because this connects to Professor Kim's talk from yesterday, that the form is exactly what you want when you're deciding whether you go or leave based on the local information. And so this is going to be, if it's bad, move very fast. Okay, is going to be the thing. But that's exactly the form that one gets. And so, and this goes back.
What is G?
G is the fitness function for the prey.
So the 0 means...
0 means the fitness function, because of the self-regulation terms, the fitness function depends on V itself, right? And so, but what we're doing here is sticking in 0 for V. And as I say, this is a very good approximation to the fitness when the prey species is rare, which is going to determine whether it can invade and persist. Okay. Okay, and so this is the idea to use this kind of a function was again Dan's, and it was inspired by the theoretical work of Amos Sakari, and he also had the very nice idea here of thinking of a family of such functions. Okay, so that we're embedding it into a one parameter family of such things using a parameter lambda. And what we want to have is that if for all lambda, if G star is positive, M of lambda of G star of U and W here will be less than or equal to D2. If for all lambda and G star negative, M lambda of G star will be bigger than or equal to D2. So when you are at 0 in the prey, 0 in the 0 in the resource, 0 in the IG predator, then G star is 0, and so then this is just if there were no other organisms present, it would be moving purely randomly at a rate D2. And you can, if you want, think of if the resources are good, you can allow it to slow down even further, though in the example of an M that I will give you at the end of the talk, D2 is the minimum there. But you could make it slower if you wanted to. And again, this has to be twice differentiable. And then the key thing here is that M lambda of G star will go to plus infinity as lambda goes to infinity, as long as G star is negative, so that you are moving away from areas where the net fitness is negative. You're going to move away from them fast. Okay, so the argument for uniform persistence of the IG prey is adapting the acyclicity argument for uniform persistence, so that the complete metric space that we would start out to base things in would be W1P plus of omega cubed. Then pi from y cross 0 infinity into itself is the semi-flow that's induced by our system. Then script A will be the compact global attractor from theorem 1, the subset of y. Y0 will be the interior y, so this will be tuples that are positive throughout the closure of omega. The boundary of y are tuples with at least one component 0 somewhere in omega. Okay, to put ourselves, so from this, since everything is drawn to the compact global attractor, we can basically concentrate our energy on just looking at a neighborhood of that. So we fatten that up. B, take an epsilon neighborhood of that, then take 2 points in time, 2 positive points in time, look at the flow under this, then close this off, so this is then compact, and then push it forward in time, and what happens, and then let S be the intersection of this set with the boundary. These things are compact, and everybody is forward invariant, but now if a component of an element of S is 0 somewhere in omega, since it's coming from something that is flowing forward to it, in order for that to happen, by the maximum principle, it has to be identically 0. Okay, so now let's let S of U and W be the subset of S where we set V identically equal to 0. A of UW, you can say, does A intersect S of UW. And then it's important here is we then need to look at omega of SUW, where here we're taking that just to be the union of the omega limit sets of all points in SUW. That's a non-standard definition, but it's only the compact invariant sets that we've got to worry about, and so this is what one has to look at for this particular theorem. So then when I do that, then of course the system reduces to just a somewhat standard predator-prey system for the resource and the intraguild predator. Okay, we know here, because the R is positive throughout omega, that the first equation, in the absence of the predator, will have a globally attracting equilibrium that I call U star. So we've got boundary equilibria U star and 0 and 0, 0, because of the form of the equation here. If U is 0, then W would have to be 0, so there is no, the only boundary equilibria in this set will be U star 0 and 0, 0. So then what one does, if you look at the principal eigenvalue, okay, what you get when you linearize the predator equation around U star, okay, if this eigenvalue is positive, so that in essence you get a net growth rate, then the IG predator is able to invade, and then the system is uniformly persistent or permanent, and there will be a compact invariant set A1 bounded away from the boundary of this set that will attract all initial data of the form U naught, W naught, with U naught and W naught both not identically 0. If sigma 1 is negative, then A1 is the empty set. But then omega of S, U, and W then will be 0, 0, 0, U star 0, 0, union A1. Okay, so then we have standard notions of stable and unstable sets here. And then the stable set being the set of points where the omega limit set is not empty and is contained in the set here. So we now need some lemmas to get our result, and the key one is going to be the following. We let U contained in S of UW be a compact invariant set. Suppose that you've got a continuous function, b of x, that is less than or equal to g of u 0 w over m of u and w for all u 0 w in the set u. So for each u and w we get a function, and so we've got this collection of functions corresponding to this set of functions. And what we need for it to be the case is that if we look at the eigenvalue, this eigenvalue problem, Laplace v2 plus b of x v2 equals sigma 2 v of 2, that then this sigma 2 is positive. In essence, what this is saying then is it's an invasibility criterion for the IG prey in the context where in the growth that it experiences is less than or equal to what it faces relative to the balance of resource and resource availability and predator pressure relative to its movement. That is, it's moving to avoid there, so that then when you take this m of u and w into account, you are taking into account that it will have very low densities in places where the m of uv gets very large, so that then this function, such a function here, will be negative but small where this is negative if this is large enough. And so, but you have to have a function that's in some sense a lower floor for it. Okay. All right. So so we need a couple more lemmas here to be able to use that, and then the conclusion is that if it can invade, then the stable set of this set U will not intersect X minus S of UW. Okay, so it doesn't go into the interior. Okay, so the second lemma is a technical one, saying that if U, again, is a compact subset of C of omega n, and phi from Rn to Rn is a continuous function, then the function f from omega closure into R defined by the minimum of phi of f of x over f in U, that this will be continuous. And then given any compact subset of C of omega cubed, we'll define G lower bar star of U to be the minimum over all U, 0, and W in U of G star of U of x, W of x, and likewise B lambda U of x to be the minimum over all U, 0, and W in U of G star of U of x, W of x over M lambda of G star U of x, W of x. Then by the preceding lemma, G star bar of U and B lambda of U are continuous. Then lemma 3 says that if U is in SUW is compact, G star U of x and B lambda U of x are as above, then if we set omega 1 to be the set of points where G star bar of U of x is positive, okay, if it is the case that omega 1 has positive measure, and that M lambda, our family of motilities, satisfies the three conditions that we had before, okay, then there'll be a capital lambda so that the integral of B lambda U of x will be positive for lambda greater than or equal to lambda, and having the integral of B lambda positive will be enough to guarantee that the sigma 2 that's associated with that is positive. Therefore, you get that you get that the stable set does not intersect the interior of X. Okay, so once we have that, then we get to the main theorem. Suppose that M lambda satisfies the three conditions, and that U star 0, 0 and A1 are as in the proceedings. Again, this is the compact global attractor for the in the interior of the UW space. Then what we conclude is if there is a point somewhere in space so that G star of U of x naught, W of x naught is positive for all U, 0, and W that are in U star 0, 0 and union A1, okay, so that you get, in essence then, you're getting a point in space where your net fitness is positive for all asymptotically feasible configurations of predator and resource that you're going to face. So in some sense, you can think of it as a refuge, as it were. There's some place where it is possible for you to to grow at that particular point. Then what one gets then is that if we look at M lambda for a large enough lambda, then V will be uniformly persistent for all initial conditions with neither U0 nor V0 identically 0. So just a little discussion of the proof. The proof is relatively lengthy. I've talked about some parts of it already. So it's based on the acyclicity theorem of persistence theory. And to use it, we need the following three things. If we have the set C, which is 0, 0, 0, U star 0, 0, and A1, that no subset of that can form a cycle. Okay, and here, when you have these compact invariant sets, you speak of them being chained if there's an orbit, say from set A to set B, if there's an orbit that goes from A to B. And then a cycle is that if you get a chain that will start at one point and come back to itself. Okay, what we have just shown about this will allow us to check this one off easily. The second, what we've got to look at a little more closely, is that no isolated compact invariant set in A intersect S minus SUV can be chained to an element of C. And then that for all the M's here in C, that the stable set does not intersect the interior. Okay, the first part, as I said, follows from our discussion of what happens in that face. For the second part, if we now look at SUV, that is the face where W is identically 0, then provided that W of S of U star 0 intersect SUV is empty, okay, this will acyclicity will apply to this face as long as this condition holds. And here we can just use analogs of lemma 1 and 3 for the function where we're just setting the W equal to 0 and hence U equal to U star. And this will work as, if lambda is sufficiently large. And so one gets a compact invariant set A2 in this interior, which attracts all initial data of the form U0, V0, 0 with U0 and V0 not identically 0. Okay, so we do have another set, namely this A2. However, it is not chained to any one of these three sets here. If we look in the face where SVW, that is where U is equal to 0, then you may show through a somewhat involved argument that all initial data are drawn to 0, 0, 0. You can't just use a simple comparisons theorem because of the quasi-linear nature of one of the operators, but you can argue that the integrals go to 0 and then argue from stuff regarding the semiflow to get the original space go to 0, but it's not completely straightforward. But consequently, A2 is the only isolated compact invariant set that's not in C, and so it's not chained to anything in C. So then we set U equal to U star 0, 0 union A1, apply lemmas 1 and 3, and the argument at 0, 0, 0 is simpler. Okay, so ecologically, the theorem says that as long as there is a location in the habitat where the conditions are favorable for all asymptotically feasible predator resource configurations, applying a strong enough fitness-based avoidance strategy will allow the IG prey to be uniformly persistent in the system. Okay, a family of motility functions that will satisfy the conditions with m lambda twice differentiable will be to take D2 if G star is bigger than or equal to 0, and then minus lambda G star E of D2 divided by lambda over G star plus D2 if G star is negative. You can check out that it satisfies all the conditions. So I want to end by just showing a couple of numerical examples that are related back to the initial modeling work of Holt and Polis. In the first scenario, the IG predator does not gain significantly from the consumption of IG prey. Okay, E3 could be 0 or small. In our numbers, E3 is a small number. Okay, so let me show that picture and then I'll come back to this. So what we have going on here, so the first graph here is the resource IG predator equilibrium. Okay, and the dark line is the predator density. The dashed line is the resource density. And now what you've got going on here is that D3, that is the motility of the IG predator, is small here. So it is tracking, as one would expect, the best of the resources, and its density is comparatively low. In fact, in places very low, where the resource is density is lower. So that, and it vigorously defends this territory from the IG prey. That is, the attack rate is very large. So that what happens here is that the fitness of the IG prey is negative throughout this region, but it becomes positive over here where the IG predator density is very low, so that then by spatial segregation, that is, it is able to persist at a lowish sort of rate, but nevertheless persist, where on the resources are lower. Now, going back to the second scenario, just slightly different, and again, here in Holt and Polis, what they were seeing here is they found that somebody went extinct in this kind of thing. And I should add here that in this picture, this is the picture when lambda is 5. When lambda was 0, so that it was purely diffusive, then you got extinction of the IG prey. So it did not appear in the system. Okay. All right. So, and the same is true in the second example. And so in the second scenario, the IG prey is an inferior competitor. Holt and Polis needed for it to be the better competitor. So E1 is less than or equal to 2. But what happens, it's able to invade persistence using fitness-based avoidance by exploiting areas where the IG prey has underexploited the available resources. Okay, so that here the IG predator has a moderate random diffusion rate. It's not moving very slowly, so it's not concentrating so heavily on the best resources, and it's only mildly aggressive towards the IG prey, so A3 is small. And so in this case then, here is again in the top curve, this is the resource IG predator equilibrium. The dotted line is the resource. The solid line, the predator, and you see here that it's undermatching the best resources and overmatching the poorest, and by just diffusing at a fairly large clip. And then what happens here is that because it's only mildly aggressive, the IG prey fitness term will be positive in the locales where the predator is actually at the largest in this case, but then so that it comes in and persists here at a lower level here, in that because it's only mildly aggressive, they're able to share sort of in the same region. Okay, with that, I will thank you for your attention.